So we developed our continuity equation using our control volume, and we ended up with this rather unfriendly partial differential equation. Even the word partial differential equation isn't very friendly. So we're going to see if we can make some assumptions that aren't too unreasonable that will simplify this equation and make it a little bit easier to approach and work with. So the first thing we're going to think about is the hydraulic conductivity. You have Kx, Ky, Kz. And what we're going to do is we're going to assume that K is homogeneous in space. So if it doesn't change in space, that means with respect to this derivative here, Kx is constant, and so there's no reason to have it inside of the derivative. If it's changing in space, we have to keep it inside these derivatives. So the K, the Y, Ky, Kz also has to be inside these derivatives if it's changing in space. If not, well, we could pull that out. And so we could basically take this out in the case of the homogeneous hydraulic conductivity, and that allows us to write the equation in terms of second order partial derivatives. So here we have the same equation, but we're assuming that hydraulic conductivity is not changing in space, and nothing's happening at all on the right-hand side. So, yeah, maybe it's not that much simpler, but at least we don't have two sets of derivatives to deal with. We have these, this is a second order derivative. We call these a second order partial derivative. Okay? So don't worry too much if you're not familiar with partial derivatives. It just means it's the rate of change or the rate of change. All right, so maybe that's a little bit better. What if we assume K is isotropic? Oops. And isotropic means it's the same in every direction, right? So Kx is equal to Ky is equal to Kz, so we'll just call it K. Since it doesn't matter what direction we're in, we'll just call it K. And so now we have all these K's here are the same, and so what we can do is we can pull those all out. If this is K, this is K, this is K, we can divide through by K, and we simply end up with all these derivatives on the left in those three directions, the x and the y and the z direction. Still have the second order derivative, but now we're bringing the hydraulic conductivity onto the right-hand side, and we've grouped it. So now you can see we've got something that's a little bit simpler. Okay? And this equation, this form of equation is actually rather commonly known. So we can use a shorthand, and we can take this whole left-hand side here, and we can use this shorthand. We can say that we've got this gradient, second order gradient with respect to h is equal to the specific storage divided by the hydraulic conductivity times the change in head with respect to time. So this is called the grad. And basically, all that means, it's a shorthand when you see this, and you see the continuity equation expressed like this many, many times. So anything that is in something like this, it means you have a second order of whatever that is in the three directions, okay? So we haven't really done anything here. This is just shorthand because we're too lazy to write everything in three directions all the time. Don't have to use this, but it's very commonly used in the literature, so I thought I should introduce it. So one more thing, what if we assume that we have a steady state? So I'm going to squeeze that in over here, so we're going to assume steady state, meaning dH dt is equal to 0. It's not changing with respect to time. So that means this entire right-hand side goes to 0. And then we can have, if we stick with our little shorthand notation, you have this. You've got this thing, it's just equal to 0. So we have some common expressions here. These are very common in, not just in groundwater, but we see them in mathematics all the time. And this is called the Laplace equation. And this version is called the Poisson equation.